In real world, videos stored on mobile devices or delivered on the internet are all in a compressed format with different compression levels, making it a challenge to restore a sequence of high-resolution frames from the degraded low-resolution frames. Due to the aforementioned reasons, traditional VSR methods do not perform particularly well on these videos. To tackle these challenges, we propose a novel recurrent and leverage metadata embedded in video files to assist in the video super-resolution process. Specifically, we first design an encoder to represent the level of compression in the input video implicitly. We then use the obtained representation to modulate the frame feature extraction blocks. By perceiving the compression level of input video, the network can adaptively extract information based on the degradation. Moreover, we incorporate metadata in the recurrent propagation process to participate in hidden state alignment and updating, enhancing the stability of temporal information propagation. Here are some challenges in performing super resolution on compressed videos. Firstly, if we directly use traditional VSR models for heavily compressed videos, it may not be able to remove the noise effectively, resulting in numerous artifacts, as shown in CVPR.23 of basic VSR. However, if we perform decompression before super resolution, it will oversmooth the details in the frames, resulting in unsharp outputs. The reason behind this is that the VSR networks are unaware of the compression level of the input video and therefore cannot make appropriate judgments based on the current degradation. We also conducted experiments to validate this fact. When training and testing with different compression levels, we found that the results were unable to strike a balance between denoising and preserving details. What more, previous work overlooked the inherent metadata present in compressed videos. In this work, we take advantage of metadata to facilitate the base VSR and enabling the model to be aware of the input compression level so that it can exert its power adaptively. The main contributions of our work include the design of an effective network that incorporates a compression encoder to perceive compression levels of input frames, a compression-aware modulation module to encourage the base model to perform adaptively under various compression, as well as an alignment and propagation process assisted by metadata. Before diving into the details of our work, let's first introduce the metadata of compressed videos. Motion vector is associated with the motion between frames. It describes the displacement of each pixel in the current frame relative to the reference frame. The magnitude and direction of the motion vector indicate the extent and direction of pixel motion, just in the same way as optical flow. Residual error is the difference between the reference frame and the current frame after motion compensation. It represents the pixel differences that cannot be fully matched after alignment, typically containing more detailed information in video frames. In the AVC video protocol, the compression level of a video can be determined by the constant rate factor, CRF, which is an integer ranging from 0 to 51. A higher value indicates more severe compression. The compression level of each frame in the same video also varies with the frame type. We extract these metadata by modifying FFmpeg. Given a compressed video and its metadata, we first utilize a compression encoder to generate a compression representation based on the pixel information and the frame type. Next, we pass it through compression-aware feature extraction module to modulate the extraction process. Then, we utilize meta-assisted alignment module to align the hidden state from the previous time step to the current time step and perform fusion. Before passing it to the next time step, we also update the information based on the current frame type. First, we design a compression decoder that perceives the compression level of the current frame based on its pixel and type information. The parameters of this part undergo a pre-training based on ranking learning. We employ a Siamese network and adopt a controlled variable approach to input paired information for learning their ranking. Each input pair consists of two frames with either the same CRF but different types, or the same type but different CRFs. We utilize the margin ranking loss to train the ranking network based on the labels. Ranking learning enables this part of the parameters to perceive the compression level of the current frame. By encouraging the ranking scores to have the correct order, degradation representation learns to encode information about degradation within it, which is the key to achieving compression-aware video super resolution. Once compression representation is computed, it is employed to encourage the base VSR model to perform adaptively under various compression. The modulation is instantiated as an affine transformation, whose way and bias are computed spatially adaptively based on the compression representation. In this way, estimated compression information is injected into the base VSR model to achieve compression-aware video super-resolution. For motion compensation, we take motion vectors as initial offsets and further refine them with the help of the residual map. An attention map is computed based on the residual map in order to refine motion represented by motion vectors. Regions with larger reconstruction errors imply larger alignment errors and rely more on refinement. Since content in B frame is heavily compressed, the hidden state computed for that frame may contain less information than others, hence causing performance degradation in the propagation process over time. To ameliorate this issue, we propose to update the hidden state of B frame as a momentum-based moving. We compare our network using metrics such as PSNR and SSM. The results are shown in table. Our proposed model outperforms most of the previous VSR methods on the three compression levels both in PSNR and SSIM. Compressed to the latest FTVSR model, our method obtains comparable performance with lighter computation and GPU memory usage. The visual results demonstrate that our method effectively preserves details while smoothing noise for different compression levels, while maintaining temporal consistency. The results of our ablation studies are summarized in table. When we insert the compression-aware modules before each convolutional layer in the feature extraction, the performance improved significantly, which could be attributed to the compression-aware design which allows the model to exert its power adaptively on different videos. When we replace optical flow alignment with meta-assisted alignment, the model will preform more accurate motion compensation and improve temporal consistency. With meta-assisted propagation, the propagation process is more stable, resulting in fewer artifacts. We also evaluated the performance of the compression encoder. We found that pre-training with ranking loss yields better results compared to contrastive loss. This design allows the model to not only distinguish different compression levels but also understand their relative magnitude. As shown in the figure, the TSNE distribution of ranking learning exhibits a certain trend along different dimensions. Introduction of frame type information can also improve the performance. In this paper, we present a novel compression-aware video super-resolution approach to deal with various compression. The key of this method is the design of a compression encoder, which implicitly model compression in a frame into representation. The pre-training process is treated as a learning-to-rank task. A compression-aware modulation modules conditioned on that representation are inserted to base models to achieve compression-aware VSR. Metadata such as Morian vectors and residual maps are leveraged in motion compensation and propagation modules to further improve the VSR performance. Extensive experiments demonstrate the effectiveness of the proposed method. Thank you for your attention.